His extensive expertise includes 3D integrated stochastic studies, prospect generation, and reservoir delineation with seismic, well, and geological data. Before we begin, I would like to give a quick reminder. Please keep your microphones muted during the presentation, and you can feel free to pose any question or comment to the chat section. And after the webinar, Mr. Mohammed will give you a time to answer every question, and you can discuss about the webinar. Now, without further delay, I'll hand it over to our instructor, Mr. Mohammed. Welcome to Mega Plus Oil and Gas Solution.
Welcome and thank you for this introduction. Good evening, everyone, and welcome to this Mega Plus technical workshop. My name is Mohammed Abdelaziz, senior geophysicist, and started actually as a senior geophysicist and now working as a senior geoscientist and structure modeling specialist. Today's workshop is not a software demo. It's about thinking correctly as a modeler. How seismic, interpretation, geology, and reservoir modeling must work together to produce decision-grade static models. Our introduction and objectives here, starting with the integrated multidisciplinary workflow with the static models, connect seismic interpretation, stratigraphic framework, logs analysis and interpretation, facies interpretation as well, with a static model construction. Building reliable structure framework, you will have a good understanding about how to handle fault uncertainties and the QC to create geologically realistic sealed fault models. And the integration from the seismic data into the static model, you will discover how seismic attributes, inversion, and horizon interpretation drive the structure features, stratigraphic framework, facies analysis, and the property, either continuous property and discrete property for distribution in the static model. Then you will have a future-ready 3D static model understanding how geostatistical distribution collaboration that can be transforming G and G data, geological and geophysical outputs to reservoir workflows for upcoming flow simulation projects integrated with a dynamic study. In such pictures, actually, the message for this picture now, giving you imagination how we can start our workflow from the seismic acquisition data, following by processing workflows into seismic data interpretations, integrated with the seismic attributes, following exact location for the faults and the horizons. All of those work, it takes a lot of time from the geophysicist in order to come up with the output of the fault framework and stratigraphic framework, and then going for the understanding of the depositional environment to create a facies classification models to propagate in the 3D seismic data integrated with the well data here. Our webinar agenda classified into 8 points. The first point, we will discuss the definition of the model and the model resolution. Second point, integration with the multidisciplinary data. And see in the third point, how we have challenges in the traditional workflow and the advanced integration benefits for the population. Then we will focus on the structure model and stratigraphic framework. Then we will take a break after the stratigraphic framework to starting the core of our modeling through journey of the properties estimations, either these continuous or discrete, and what is the algorithm using for this property estimation. Then we go for the most important part, which is the end part of our webinar, for the modeling QC, volumetric, and uncertainty analysis that we captured from our static model. Starting with the model definitions, to question what is a model? A model is a space A model is not a map, is not a surface, is not a volume. It's a space. You know, in our reservoir model, we subdivided the subsurface into a 3D geocellars. Each cell, it's a space, have an X and Y and Z. And each cell hold single discrete property value, like lithology, facies, rock type. Then we are going for the continuous property for populating within each cell. And the shape of the cell and the size of the cell, in addition, the orientation of the 3D grid are determined by the available data you have and the modeling objectives, and that we are going to illustrate in the next slides. Model resolution. You know, the size of the cells itself determine the model resolution. So the resolution here is a decision. It's not a default. So you can control the resolution of the model. I will tell you how in the next slide. But I need to illustrate for you the geological model is a collection of cells which forms a 3D grid, okay? Then you can populate with the rock property information, such as if you are populating with the continuous property like porosity, permeability, water saturation, net growth, shale volumes. For sure, this is a function of a discrete property like facies, understanding first the viewer background about the positional environment you have, which system you are working for, low stand, high stand, because it will affect on the geometry of the layering after that. I will tell you in the next slides. And also, you have lithology. You can make it a property and the fracture density as well. So as I mentioned for you, the size of the cell determines the model resolution. So here is some examples from try to integrate the surface data into subsurface modeling. The model resolution here, as I mentioned for you, is the decision. As you can see here in these formations, actually, to transforming this data into subsurface data, you have to convert it into cells, okay? And each you can identify the number of cells. It depends on the number of detailed or the degree of detail you need for your model. So it depends as in your objectives, okay? So for example, in this point, in these formations, we have multi-layers, so I need more details. So I can make decision as a geomodeler, okay, at these formations, I need more details, so I need to be cells, very small cells, in order to populate the facies and the probabilities within it. Once you go with this arrow, the model resolution, it will be decreased. So it depends. And also there is another point for compromising the time of the simulation. So you have to have an compromise, a compromise agreement with the reservoir engineer about the time of the simulations. It depends on your objectives. Because once you have very detailed small cells, you have a very lot increasing of the informations, so it takes so much time in simulation. And coming back to some definitions of the geomodel, geomodel is a numerical equivalent 3D geological set of maps. And these maps are complemented by description of physical quantities in the geological interval of interest. Physical quantities here means the facies and the properties. All of the physical properties, it transforming into numbers inside the cell itself. In today's oil and gas industry, the models are very required, so much required to be an input for reservoir flow simulation programs in order to identify the uncertainties. The objective here is to identify the uncertainties. I will tell you the beneficial of the uncertainties for the decision making of the high level of the reservoir management. Actually, an actual reservoir can only be developed once, and any mistake can be very tragic and wasteful and expensive during the static model. Here the integration, this image showing for you how much integration you have in order to come up with a 3D static model. Model is a discipline based on data analysis, integration across different disciplines, starting from the seismic interpretation, as I mentioned, going through logs analysis from the petrophysical interpretation, then going in detail for core and core data, because core data is it has some special core analysis in identifying actually, in more accuracy the permeability and porosity. Going with your background about the outcrops, because outcrops here is telling you what is the depositional environment you have, what is the structural regime you have, to come up with a geological conceptual model and integrated with the field and well performance data you have in order to feed back the dynamic models to come up with the integrated 3D model, starting from static model to the dynamic model. What are models used for? Model used for one of the important, as I told you, it considered as input for reservoir simulation. So this is used for dynamic simulation, used for the accurate 3D volumetric calculation, because all of us can do this volumetric calculation, maybe from our maps, but okay, map-based volumes. And then also it will help you in the future well planning, because once you are planning for the well design in the 3D statistic model, you will know the best location for structures, you will know the best location for the stratigraphic trap, you will know the best location for porosity and good fishes. And also very useful in fault seal analysis, especially if you need to go for the downthrown side and you already produce from the upthrown side, you need to make a fault seal analysis. Once you go by the V-shale population in all the segments of the blocks, it will help you identify and analyze the field fault sealing exactly. To end with the 3D visualization of fine-scale geology, integrated fishes, porosity, permeability, whatever you need for propagations, it depends on your objective. And finally, it will help more in flow simulation. What is the best stage for model? All of us, we know we have 5 stages of the life cycles, field life cycle, I mean, starting with the exploration through discovery and evaluation. It takes from 5 to 10 years. It depends on the agreement from area to area and from country to country. And once you have amount of reserve, once you have a good data, you have decision to drill, and you are transforming into the development stage, which is the production and facility design and implementation for those. In such way, you are going for productions and finally going with abandonment because of the decline curve. The best stage here is a part of evaluation, development, and production phases. This is the best stage for doing your model. Is it possible to go for exploration? Yes, you can do it in exploration, but you will have a very high degree of uncertainties because you are lacking of the very important data. You are lacking from the well data enough to manipulate and to compromise your population and distribution. This slide, I like this slide in this webinar. Why? Because before anything, you have to have an objective, okay? What is the objective of reservoir modeling here? Once you have objective, okay, you determine the approach and technique that the modeler will utilize. So the modeler should know the objective of this of the modeling, okay? We have, as I mentioned, different stages of the evaluation, starting with exploration, appraisal, development, and reservoir management. In exploration, appraisal, development, okay, we all agree this is an example, okay, for the objective. We all agree about we need to estimate the reserve. We all agree about to estimate oil in place, okay? Once we go for the appraisal and development, the objective increasing, and we need to know field development plan strategy, optimize with numbers and emplacement. We need to have a philosophy for completion strategy, production strategy even. All of those stages, we need to identify and quantify key uncertainty, okay? From stage to stage, you have uncertainty, okay? But your roles as a geomodeler or as an organization, okay, you need to decrease this uncertainty by adding new data, by by applying more study, by applying seismic, for examples, okay? And in reservoir management, you need to improve and update best scale, I mean. Even you need to update the history match, find attic oil, improve operational strategy, and you need to drill and new wells. So it depends on your objectives, okay? Your model will determine the technique that the geomodeler will utilize. All of us, we know, okay, garbage data, garbage model, garbage results. And in other way, reliable data, okay, if you have a reliable data, but you have a garbage model means here, it's not reflecting the geology, it's not match with your data, well data, and at that time you will have a garbage results. Model workflow. I will give you a big picture now about the model workflow, starting from the input data, quality control for the logs, checking the thickness map, structure maps, faults, and then going for the depositional environment, depositional systems, try to understand the sequence stratigraphy because it will reflect the geometry of layering, as I mentioned to you. Okay, going for the geocellular grids and upscaling for the logs you have, and using the best algorithm to upscale your data and try to match very high degree of matching between the upscaled and the log data. Trying even using the geostatistical approach, using the variogram in order to guide the software to distribute the data in the desired directions and azimuths. Okay, because this step is taking so much time from the geomodeler in order to before propagating the fishes modeling and the petrophysical modeling. Geostatistical, we will discuss in details and understand the concept of the distribution. Before going for the fishes modeling, you have to guide the software in which way they can distribute, in which way, in which direction they can follow. Okay. In addition, if you have additional variables, data like seismic attributes, seismic inversion, machine learning techniques, how can use all of those data in order to helping you trying to make a best fit fishes modeling that respect the geological and the conceptual model in your data and matching with the well data you have. Then going for the continuous property distribution in as like porosity, permeability, water saturation, heat growth. It depends on the needs of your population, because sometimes we don't need permeability, sometimes we don't need net growth. I will tell you in the propagation slides. Okay, all of such distributions, in order to have a 3D complementary volumes that will help in assess the volumetric, that will help in also measure the uncertainty and try to make analysis on this uncertainty to take a good decision for the reservoir management. After that, you can export the volumes into the dynamic model for doing a flow simulation. And by the way, it's not the workflow, it's not easy like that. Actually, it's iterative workflow. Sometimes I have to come back to the seismic interpretation, adjust some faults, and come back again in the variogram analysis, especially in data analysis. It takes so much time adjusting the errors and to come up with matching with the dynamic simulation. Geomodel types. This is the normal 2D deterministic models. Actually, you are using the well data here in order to mapping the 2D data without respect the area in between the wells, like that. So it going by the average weight interpolation between well and the others, so going like that. In the second type of the geomodel type, it's a 3D geostatistical models. So we will discuss more in deterministic and statistic and geostatistical definitions and the difference between both all of them. But here just overview about the results and outcomes from the 2D and 3D model you have. This is an example from porosity propagation in the 3D distribution. Going now for the beneficial of multidisciplinary input data, because this is the input data we need. We need to make it reliable, matching with the geological sense. This is the most important. So we need to have enough information from different disciplines in order to come up with the realistic geological static model. So geological data utilizing reservoir characterization here, you have different data sources. You have well data, borehole logs. You have cores, outcrops, thin section. The more data you have, okay, the reliable model you get. The more data and the trusted data you have, the more realistic model you get. So for sure, we have the wells data. Okay, well data is truth, but well data is not sparse. Okay, it's already sparse. It's not continuous in directions. It's not follow the fish's directions. You get my point? So you have also uncertainty. It depends on the amount of wells you have. It depends on the seismic data you have. Seismic is continuous, but indirect. So sometimes you have, it's not telling you directly about the properties. You get my point? It should be have some analysis like seismic inversion to telling you some kind of confidence about the distribution of property. For example, from acoustic impedance, we can know the porosity here. So a lot of data sources we need to have it in input data for the static model. And data sources also come with the professionals like geophysicist, petrophysicist, sedimentologist, geologist, biostratigrapher, and structural geologist. And here is some kind of process like depth conversion, sharing between a geophysicist of the seismic processing here, and petrophysicist and seismic interpreter, and the quantitative interpretation for probability modeling, also sharing between the geophysicist and the petrophysicist. Structure interpretation sharing between seismic interpreter, geologist, and structural geologist, and the biostratigraphic also sequence stratigraphic interpretation sharing between geologist and geophysicist and the biostratigraphic. And here is a lone, scope reservoir engineer responsible for volumetrics, simulation, development options, field development plan, and well plans, integrating with all of this in the static model, and he is responsible for dynamic model. So all of those professionals will come again, okay, in the closed loop between the geomodeler and the reservoir engineer in order to come up with the integrated static and dynamic models. What is the seismic data provides information for the static model? It's provide structure framework, stratigraphic framework, kind of facies classifications, variation in rock properties and the fluid types across the reservoirs, telling you where is the geology, okay? Validation on fluid and the pressure change if there is some faults at the compartmentalization, okay? Identifying sweet spots related to the different reservoir conditions because it will have different pressure and the fracture properties as well. What are the challenges in traditional workflow? We have a lot of challenges. I'm trying to summarize some points for you in this webinar for overview about it and how we solve it in order to come up with good, reliable data. So we have challenges in depth conversion uncertainties, fault framework mistypes, and the limited feedback loop between interpreters and the modelers. Depth conversion uncertainty here, translating seismic data in time to depth conversion using the velocity model, okay? The velocity model, if it is incorrect, the impact here, it will be mispositioning of geological feature in the model, okay? Number two, fault framework mistype. If your fault is misalignment, inconsistency between interpreted faults in seismic interpretation and how they are modeled in the static framework, the impact, it will be an errors in structural geometry affecting after that the flow simulation and reservoir connectivity. And the limited feedback between interpreter and the modelers, lack of iterative collaboration between geophysicists or interpreters and reservoir modelers, actually its impact, it will be misunderstanding or missed opportunities for refining interpretations based on modeling needs. So this is the challenges that we faced in my experience, actually in different scope and different projects. So I would like just to share with you some solutions, addressing some solution with you in order to avoid it in your projects within the static model. See, this is an example of the velocity model. Here, the directions dipping northeast, and the direction in depth conversion changed totally. So they are trying to make a depth section with velocity model 1, velocity model 2, okay, confirming the depth now, and finally this is a depth section with the final velocity. So what is the error here? The error is the velocity in the velocity modeling. So my recommendations to use more robust velocity models, try to incorporate well velocity data like check-shot VSB, which is a solid data to constrain time-depth relationship. Because I will tell you, because some errors in interpretation is not due to interpreter, it's due to velocity model problems. So in sometimes we need to make a probabilistics or a stochastic depth conversion to capture the uncertainty by generating multiple realization of depth models. Because in such way, once I go with different velocity models, okay, and they make it as a probability and doing, some uncertainty analysis, So the analysis of the uncertainty here telling you where is the problem or where is the maximum, because it will give you multiple realizations, and from these multiple realization you have an error in, for example, velocity picking. So you know that in 10 realizations you have error in velocity picking, and in 5 you have in vertical in depth conversion and the sonic lack of sonic data, for example. So once you are going by the uncertainty analysis, you will know where is the, through applying different kind of realizations, okay? Because you have maybe, okay? So you have different scenarios, 1, 2, 3, 4, something, for example. So for 1, you have uncertainty. For 2, you have uncertainty until 4. So all of these in uncertainty analysis, you will have the better choice to judge where the uncertainty come. And try to make iterative calibration. So use 𝗦𝗁𝗶𝗃𝗀𝗃 iteratively update and validate depth models. So this is the point of the depth conversion, uncertainty solutions. Now the fault framework 𝗦𝗁𝗍 solutions. How can we reducing it? Try to integrate fault modeling framework. Try to align fault picks actually across discipline using shared platform. Why fault picks? Because the fault picks here, it has the formation fault cuts and the stratigraphic units. It is actually, by the way, interpreted. It is not solid data. So at each project I have worked, I have many interpreters for fault picks, for stratigraphic units. To solve these problems, this should be shared in the shared platform like Petrel or 𝗬𝗀𝗃𝗃 for geophysicists, for geomodelers, in order to be one. The agreed one should be shared. Okay, this is one. This is the solution here to avoid any misties. Okay, and the second solution coming from the using of AI technique, which is snap to seismic. Refine fault geometry by snapping to seismic events during modeling building. So during modeling building or during seismic interpretation, you need to make some kind of AI help you. These points, it's called the seeds. It will keeping you to stay on the same event. Okay, this is kind of saving time, accuracy more. For sure, you will have your experience, but should be now we are in the AI techniques all over the any scope in the seismic, in our world, in everything we have AI. So we have to use it. We have to help to get his help in identifying the same event all over the cube. Because sometimes the map is very beautiful. Wow, there is no error in the map, but actually, is it right? If the fault is correctly, you get my point. If there is a geological sense, what about the fault throw in the geological sense? What about the hanging wall truncated problems? So a lot of problems telling you where is the uncertainty coming. Okay, so and in such way, and for the fault validation with the well data, try to use well trajectories and fault cuts to check and refine your fault positioning in the model. The third point, improving the feedback between interpreter and the model solutions through collaborative multidisciplinary teams. So we have to encourage, the project manager, the organization, encourage the interpreters and the model and engineer to work together, to work in the co-located groups. Okay, we need to close this loop. So the looped workflow here allow model updates to inform reinterpretation of seismic and vice versa. Sometimes I need to refine the fault interpretation. Sometimes I need to refine the fault cuts in the picks. Okay, so the solution even here try to make shared digital platforms. So once you use the integrated software environment, it will allow for real-time collaboration and data sharing. What is the advanced integration here before starting our static model? Advanced integration here, actually, it's related to the seismic background, because the seismic is continuous property, as I mean. Seismic data is a continuous even between the wells. Okay, so and this is the only way to follow the data in between the wells. So once you have a good analysis for seismic attributes, sometimes you are using machine learning classifications, and there's certain type of seismic inversion, and for sure the dynamic data integration. Seismic attributes analysis, machine learning, seismic inversion, they have outputs. Their outputs considered for the modeling as a secondary variable property. So this is secondary variable property is very useful. It's very useful, especially in the fishes population, because once I get the second hand for after 𝗪𝗏 analysis and data analysis, I'm telling you here, this is the second input data. You can use it, you can integrate it before doing your fishes modeling. It will help more. I will show you in the fishes modeling. Here is some example of seismic QC attributes analysis to validate your seismic data, because seismic data is amplitude, phase, frequency. So once you apply the seismic attributes like coherent, most positive, most negative curvatures data, in order to identify and validate the fault locations. Some attributes does not, capturing the other direction of the faults. Other attributes can be going more much detail. It depends on the data, and it depends on your objectives of the interpretations. In using machine learning or the fault horizon interpretation, also whatever this is manual or semi-automated picking of faults and horizons, using these seismic attributes. This is for examples here by seismic attributes. This example, time inline, cross line, and time slice. Okay, and using AI assisted interpretations after detecting the salt domes, you are telling the software through AI buttons to extract for you the salt dome like that. So also this is one of the integrations. I'll tell you the most recent update machine learning classification, which is called RGT seismic model. This is relative geological time. The best thing in RGT, it's actually integrating a chronostratigraphic volume where every seismic sample is assigned. It's relative to deposition age. It's now respecting the depositional model. It's respecting the sequence seismic stratigraphy. So RGT is a vertical derivative and is so much sensitive to stratigraphic discontinuities. For sure, it needs your help. It needs your guide. Once you guide the software to tell him, this is a sequence boundary 1, sequence boundary 2, and I'm working on the low stand system tract, go for the RGT model, okay? Give him some input data. So he will give you the special gradient of the model. They will give you the chronostratigraphic interpretations, okay? It's respecting the stratigraphic discontinuities, and for sure it will reflect on the vertical displacement of every horizons in the RGT model. Will also compute it, even if you are working on the poor seismic data. You need to review this seismic model. You need to try with your data. This is my recommendation for you. And the best platform here. It's not for marketing, but this is for to be used if you have a chance to use ValueScan. This technique very useful, especially if you are working in the sequence stratigraphy and you need to know the relationship between the structural framework. The third advanced integration here, the seismic inversion. Okay, here is the example of post-stack seismic inversion techniques. I try to capture for you the best type, which is model-based seismic inversion after a long journey of wavelet extraction and see the well here. Well here is drilled in a good structure, okay, but in this example in a gas field, and they need to understand the porosity. They need to understand the porosity results of this well and trying to integrate with the seismic data. So they make model-based inversion using this well and other wells in the area. They make a cube for acoustic impedance because you know the acoustic impedance is related to the porosity fraction. So after that, they converted to porosity prediction to come up with the integrated porosity all over the seismic cube. So you have a seismic cube of porosity predictions, and this one, as I mentioned to you, it will be as a secondary variable property before doing the petrophysical modeling. So it will very helpful for your static model. This is the third type of the advanced integration. The last one with the dynamic simulation here, it's called sensitivity analysis. Sensitivity analysis, it comes, as I mentioned for you, our workflow is iterative. So after you know run volumetrics and run flow simulation, they found you have area is 20% less recoverable oil. Okay, and you already interpreted the model A fault 50 meters east, the red one, and the horizons, okay? And you already you have another scenario of interpretations, 50 meters west, orange fault horizon and the interpretation with this drag on the fault, okay? This is normal drag here. And they discovered the dynamic model reservoir simulation, the fault A, okay, using in the model gives 20% less recoverable oil. So this is already accumulated, and you already produced from this compartment. So you need to refine again your interpretations. So at that time you will update your model for the orange fault and coming back to dynamic simulation. So most modern geological modeling and reservoir simulation platform allow sensitivity and testing and analysis like Petrel, RMS, decision space, and the T-Navigator. Now we will focus on the structural model which is a backbone of the static model. The structural model here provides a container for populating fishes and rock property, whatever this property, as I mentioned, discrete or continuous. What is required? It is required interpreted horizons, okay? Required faults and internal layering scheme. So from 2D grid to the 3D grid to the 3D cellular grid, okay? As it depends on the model resolution you have. You need to have a fault framework from the interpretation. So it's a major control on the reservoir volumes and the flow behaviors. Why faults modeling? I have 3 questions in this webinar. This is the first questions, okay? The first question is why fault modeling? The second question is why facies modeling? And the third question is why petrophysical modeling? The answer, it will come on the slides. Starting answering the first questions, actually, fault modeling, it's a considered structural control. So without fault modeling, your maps, it will be wrong. The gross rock volume, GRV, it will be incorrect. Hydrocarbon column height may be miscalculated because it affects on the volume height, the area of upthrown or downthrown that bounding by the fault. Fault have a good relation with the compartmentalization because fault is divided reservoir into compartmentalizations, as in these examples. So in the compartments here, it's different. It has different pressure. So if not modeled, you will assume full connectivity, okay? And the pressure predictions become unrealistic, and even the wind interference analysis becomes wrong. So this is now the beneficial of fault modeling. Fault modeling acts as a flow behavior in dynamic simulation. The sealing fault delaying the water breakthrough, okay? And the transmissive flow connectors here will accelerate the production from the water. So without fault modeling, the history match becomes unstable, and the reservoir engineer artificially will change the permeability to compensate. Also fault modeling very important in assessing volumetrics and reserves, because fault is trapping the closure area. Fault, it's making hydrocarbon contact levels, okay? Define the hydrocarbon contact levels and structural spill points in expiration blocks. So if faults are misplaced, you may overestimate or underestimate the reserves. And here is an example from fault gauge along detachment fault, because that detachment fault should be in shale reservoirs. So I'm expecting you, and you can expect the shale smearing in the fault plane between upthrown and downthrown. Faults can be created from different data input. You can digitize the fault. You can create the faults from fault sticks that already come from the fault sticks in seismic interpretation, from the seismic, I mean, from the polygons or well tops. Okay, if you have a fault cuts, it will help you to tie. You can digitize on the surface. Sometimes the interpreters make a surface without fault sticks, so the geomodeler should digitize on the surface. Okay. Even you can digitize it on the 3D lines. So this is a seismic, this is a horizon interpretations, and this is the gap, and you already pick the pillars. Okay, we will do that in our course in details. Digitizing on seismic interpretation, which is a normal part, and even you can digitize it on cross sections after cutting through intersection lines. So there is also another point, tying faults to well cuts, which is very important here, because the geologist will give you the fault cuts, and the geomodelers will try to tie this one. And there is a good option for I think in many softwares now to look the fault sticks at the well tops. This is actually for in terms of the static model, it will validating and demonstrating your seismic fault interpreting using well data. It will ensure the fault geometry and displacement seen in the seismic to be as consistent with what the well penetrate. Okay. It is actually critical for reducing uncertainty in the structure, especially if you are making fault seal analysis in juxtaposition and compartmentalization. Compartmentalization here means a compartment in upthrown and a compartment in and downthrown, because as I mentioned to you, the fault is classifying the model into compartments with different pressure, maybe have a kind of communication of pressure. Also, I captured for you some problems, some challenges and solution here, in order to imagine how the importance of the fault modeling. The problem here, in such example, it's come due to fault seal analysis, and the sealed fault framework may look correctly geometrically, but actually it's interrupted geological rules. So the issue here in like structure truncation and fault juxtaposition, it will have some errors, especially in the hanging wall, okay? So and also you need to check the fault through as a kind of sense, geological sense, because sometimes it's inconsistent with the stratigraphy or regional settings. Okay, so you have to check this. So in the solution here, we have to make a fault juxtaposition analysis. Either you can do Allen diagrams or throw versus depth plots, or you are making run horizon truncation checks against the fault planes. This is in the modeling, trying to compare the regional stress regime and analog data from the surface outcrops. And you can use automatic QC tools in software to flag where is the geometrical error that inconsistent with the geological sense. In such examples here, you have V-shale distribution, V-shale using it from the petrophysical, using as a property in reservoir modeling, and the V-shale here this is along the faults, different up thrown and down thrown, and right here the maximum cross fault V-shale. The yellow areas sand juxtaposition, and brown area it's indicate to sandy shales, which is very important now for analyzing of the fault seal analysis, sand shale or shale against each other along the fault plane. So this is actually this approach we will also discuss it more in our course. One of the problems here also the extrapolation distance. The extrapolation distance of the hanging wall does not fit with the geological sense. It have some anomaly like here. Either you go by the normal solution, okay, it depends on the software you are using. In Petrel, there is two ways. In corner point here, corner point grid, you can manually adjust the horizon by changing the horizon fault lines, okay? And also there is another way in structure framework. You can change the extrapolation distance of such level with the relative fault that making the problem on it. So it's a lot of problems you will face in the structure modeling. It takes a lot of time, actually, especially if you are working in the complex regime of the structures, but taking your time in such stage, because this is a controlling your propagation after that. Stratigraphic framework now. The stratigraphic framework actually the structural grades feeding fishes, okay? The structural grades heat coming from the combination of the structural and stratigraphic features, because it will feeding fishes. I'm going in my slide as a workflow, okay, for you to understand very well which step we are starting, step by step until the end of the volumetric calculation and stratigraphic framework. So we will address here the 3D structural grids. As I mentioned, for new structural grids feeding fishes and the property models, grids act as the foundation for populating. So you have fishes modeling, the positional environment leads to fishes, petrophysical models, porosity, permeability, saturation. This is actually, we are focusing now. This is our objective during our making of the horizons. So this is the surface outcrops, okay? And this is the structures, and this is, so it has some layering. So in order to convert the geological assumptions and information of such area into numerical 3D cells, okay, you need to have a fault framework, you need to have a skeleton data, and in order to make a stratigraphic framework in the seismic scale. This is the horizons. Then once you go to isochord scale, using the isochord thickness maps in order to make a zonation, okay? And you need to go more inside the reservoir by making the layering in detailed scale. But the layering here, it depends on your conceptual depositional model in your area and the sequence stratigraphy study in your area to understand very well the unconformity surface, to understand very well where is the sequence background that will control the geometry of the layering, either to go on lapping, top lapping. I will tell you in the next slides. The stratigraphic framework and static model actually mainly depending on the stratigraphic sequence stratigraphy. Okay, it defines how layers are organized in space and the time before petrophysical properties are evaluated and even before Fish's modeling. So once you know your sequence stratigraphy, sequence boundary, the flooding surface, okay. For example, this one, it will be based on lab. This is in layering. I will tell the software follow top. Okay, so all the layering, it will follow the geometry of the flooding surface here. But if you have sequence boundary here and the flooding surface here, depending on the system tract you are working for, so at that time you will have top truncated, so you will follow the base for the flooding surface. If you have two sequence boundaries, okay, so you will have a proportional relationship between the layers, inside the layers. Sometimes you have depositional horizons in between two sequence boundary. At that time, you will handle the layering in such zones. It will classify it into two zones, and you will handling the geometry of the layers. What is the aid? What is the cooperation here? The cooperation comes also from the seismic data interpretation, especially if you have a regime combined structural and stratigraphic traps. So it will help you in identifying the geometry of the layering in the static model. The stratigraphic framework approaches actually three types of stratigraphic framework, starting with the layer cake model. It's a simple, it's a flat, which is not realistic, to be fair with you. Unrealistic connectivity you will get. But once you are using the sequence stratigraphy framework based on the depositional sequences, you will honor erosional surfaces, and your model will be more geological realistic. And if you have an object-based, okay, so you are going based the framework, depends on the object you have. Either you have channels, you have loops, you have clinoform, you have refall build-ups. This is most realistic for complex systems. So I'm trying to make you imagine how the efforts for each discipline, having this integration with the static models in order to come up with a reliable static model. The last one, the properties estimation and 3D distribution here, we will start, but I prefer to take 10 minutes break. Is it okay for you? Because the upcoming one, it will have a lot. It will be heavy. So I need to take 5 to 10 minutes break. Is it okay
Yeah,
with you? Yeah.
I
Okay.
think it's okay, and in 10 minutes we can come back.
Very good. Very good. Okay.
Thank you.
Thank you. Hello, everyone. I'm ready if you are ready with you.
Yes, just give me a second so I can record again.
Sure.
Okay, you can start.
Now we will talking about the properties estimation and 3D distribution, starting with the scalable logs. In such examples, I need to show you the different scale up for continuous property and discrete property. This is example from well data you have. This is a well track, okay? This is the porosity data coming from the petrophysical analysis from petrophysicist. And this is a scale-up well logs, okay? This is a facies interpretation, and this is a scale-up well logs for the facies. Facies here, it's a discrete property, okay? And porosity here is a continuous property, like porosity that has value, that have the difference between continuous and discrete here. Discrete here, it's just one value for the cell, okay? And it's not actually, it's a definite value. But the continuous here, it's it having values like 2 and 2.5, 20, 20.5, something like that. All of us know about the resolution of the logging data. So you have in logging data each 15 centimeter data. So if you are going in upscaling each 15 centimeter data, okay, you will have very, very dense cube modeling, I mean, and it will take so much time. It will make maybe it will take months to run any simulation. So that's why there is a scalable logs. This is a beneficial of scalable logs. This is taking the averaging of your raw data. As you can see here, it's classified, this part is classified into 1, 2, 3 parts in taking the average, and also in such a zone or the sand here, it taking also three cells, 3 vertical cells, I mean. So this is the upscaling now, okay? You are upscaling the property into averaging values, okay? And after that, you need to check the upscaled in histogram with the raw data. Geostatistically, it's apply. You can work with it, okay? You can go by your data. In discrete logs, actually the same. This data is classified into 3 cells, and then also making upscaling for the facies, and you can make a correlation between the raw data and the upscale cells. So the percentage is very near by each other. In such examples, we have 1, 2, 3, 4. We have 4 kind of facies, and in this one we have 1, 2. We have 3. That means there is somewhere in other area having this 4th type of facies. So this is representing the area, okay? What is actually what we are going for, the concept of biasing bias data in discrete logs? As I mentioned for you, this is facies, and this is inside the cells we are classified, the upscaled depending on the value of each facies. Once you have this is, for example, for raw facies like that, we have sand, we have shale. At the basal part, you have the shaly, but our algorithm and our, because this is the limitation of the modeling, okay, you are using the bias of most of. So you are telling the software, once you have a most of inside these cells sand, consider it all sand, and the same in each cell like that. And this is, the concept of the bias data, most of, I mean. So after that, you will have a raw porosity here, okay? And upscale the porosity, because it's so much detailed, so much, high resolution logging, see? But I'm going by the averaging, trying this many times until you reach. Sometimes some of the geologists do not agree about this. So, okay, no, I'm respecting, I need to capturing exactly the sand. I need to figure out this as a shale. So I have to go back for this classification of the cells and making this is different cell in order to come with this solution. So this is iterative approach until we satisfying the upscaled facies and the upscaled property for porosity, or any continuous porosity, or a continuous property, I mean. Here, before going for the facies modeling, I need to going with you step by step from the stratigraphic to the structures, and then going for the upscaled for each well, okay? So you have upscaled facies in each well like that, okay? So, and you need to make a VPC, vertical proportional curve, which is a main calculation in before doing your static model, because the VPC here, I will tell you the concept here. You have 1, 2, 3 in the first cell here, which is encountering the sand. Once the VPC to extracting your VPC, you are telling the software, and the software will search in cell number 1 in all the wells, about the upscaled facies or the upscaled property in order to come up with the averaging proportion like that. So this is a vertical proportional curve. So it's coming from the well data. This is coming from the well data, and it will be a main guide for the modeling, because the modeling, whatever the algorithm you have, okay, you will have in layer number 1, okay, 50% channel, 10% Levy, and the 20% shale, and you will find whatever the algorithm you have in the layer, in the basal layer, the 80% of the shale you have. Should be this. So this is now a guide for him. It depends on in the data be in between the wells, but the percentage he will understand. He will keep this. Okay. After that, which is a very critical point here. So the property curve. The probability curve is telling you, also is expressing your VPC curve. Once you are doing the VPC curve, okay, you are doing for the property curve in order to know the probability of the facies you have. There is a very important secondary derivative variable here, which is acoustic impedance. So you are telling the software, you have a secondary variable here, okay, the acoustic impedance. It's reflecting in the x direction here. So all of these cells reflecting the value of the acoustic impedance cube. So for example, in 15, this is, I cannot read the number very well, okay, but this is 15,000 maybe. So above 15,000, it will be shale, okay? And if you go for this value, about 7,000, you will have a probability, please focus on this, you will have a probability of silt to be 20%. You will have a probability of sand with different, it depends on the location you have. You have a probability of the shale. So that's why the model gives you multi-realization. I have seen a lot of messages. I cannot read it now, but I will. I promise I will reply on each message. But please be patient with me, because it will be integrating with each other. Okay. So if you try to understand with me the VPC methodology and the property modeling curve, integrating with the second derivative, whatever this is, AI cube, coming this from the seismic inversion. And this is now the advanced integration, what I mentioned for you. But still for you, you have a different realization, multi-realization. It depends on the algorithms. I will tell you how. And this is one vertical layers. And for one vertical layers should be the facies codes and the facies percentage should be 100% for all, for one the vertical layers, okay? So now let's go for the critical point here, which is a variogram methodology. The variogram, it will answer for you fundamentally questions. How similar are probability values as a function of distance and directions? Because each value you have, for example, you have some wells, okay? Different wells here and wells here and wells here. And what about the variance distance between each other, okay? Excuse, I need to go for the bent just to go with you in here. Sorry. So now I'm sharing my screen. I'm using now the bent software. I need to going for you for the variogram understanding. Okay, so if you have different different well location, we have where this is the well location you have, okay. What is the variogram measure? The measure the similarity between the variance. So the closest variance to we will start with it. The closest distance, okay. And if they have between this one similarity, they will start with the variogram algorithm, and it will consider this is a lag one, okay. So for example, lag one is a 5 meter, okay. So the software will search each 5 meter or each from the 0 to 5 meter. If there is any wells has a variance, has similarity, he will capture all and the point like this. Then the lag number 2 from 5 to 10 meters. If there is any wells, the distance between them from 5 to 10 meter have a similarity, they will put the point number 2, and so on till they have the maximum variance. Suppose he reached to the lag number 6, okay. I will explain with you what is this tolerance angle here, because it's searching now in 3D, searching in X and Y, respecting the azimuth direction. It depends on the search cone, okay. Search cone, that is the distance he are searching for about the well data you have. This is from your well locations, and this is from the logs data inside the well. For example, if we are making a variogram for the porosity, okay. So he was searching the value that nearest between each other. So it's a function in distance and values until he reached the maximum variance, which is the cell here. And the distance to reach to this cell, it's a maximum range, okay. And then you are going for the variogram, experimental variogram like this. So, and what about the nugget? Nugget here is the closest distance between the wells to capture the variance. So,
Mr. Mohammed, just in case
yes.
we are still looking to your screen showing the paint.
Sorry. Yeah. Yeah. Let's. I think now it's shared now.
Yes. Yeah, we can see your screen. Thank you.
Okay. Sorry for that.
No worries. Thank you.
Okay. Thank you. So the variogram, as I mentioned for you, is a quantifying special continuity of the geological property. So as I mentioned, I will repeat it again because it's very important to understand the algorithm of the variogram. It's respecting here the distance versus direction. Distance versus direction and value for each point. He will consider the well data. He will consider the well data and try to get a variance between the closest distance, which is a negative here, and searching for it along all the wells you have. For 5 meters, he will put it, for example, I mean, from 5 to 10, he will put the second point, and 15, suppose you reach it for the 50 meter, which is a lag distance, and there is no similarity between the well data and between the logs data after that. So the similarity of the variance stop here, which is the cell. In such point, the variogram understand now his inputs to put the negative, okay, to put the cell, to put the range, and then you will go for the doing your match through try to match the experimental variogram data to the well data you have. I will give you more examples if you have questions. I have different slides after the webinar. We can discuss in more details about it. But for the time being, you know, it's in static model variograms, how phases extend. He's telling you how petrophysical properties propagate and how geological realism of the model, okay, itself, depending on the searching cone, depending on the direction, depending on the distance between each other. All of this, he is quantifying the spatial continuity, the spatial similarity. So it's going from point to point. You know, this is, you are going by horizontally and going vertical. Vertically, and I don't care about the vertical because the vertical resolution, it's coming from the upscale well logs, but I'm discussing the horizontal variance, the horizontal variance. For example, I have types on static models. For if I'm applying variogram for fishes variogram, okay, so I'm controlling fishes geometry, usually long range horizontally and very short range vertically, which is capturing from the zonation thickness and the well logs. But strong anisotropy now, if you have a fluvial channels, so it's the major part, it will be 15,000 meter, which is a channel axis, and the minor is a 400 meter, and the vertical, which is a thickness here. Okay, I am coming back to the bent. If you can see, I need to. Okay, I can draw it here. You can see my screen, I think, right? And if you have a picture like that, okay, this is a channel, for examples, and you have the sanded channels like that. So the maximum, the channel axis here, it represents the 1,500 meter, which is the major variogram, and the minor variogram, until you finalize the sand, it will be 400 meters. So this is now the understanding how they can capturing the fluvial channels in the variogram. In such way, you are detecting the azimuths, you are detecting the major extension till finding the last similarity or the last points of variance in both directions, in major direction and in minor directions. For vertical thickness, you can know it from the well logs and zonation segments. This is for fishes variogram. For petrophysical variogram, you can apply it within the fishes because the petrophysical variogram, it will be different per each fishes because it's a function of the fishes. So, for example, sand porosity, long range, and if you have a shale porosity, you will have a short range plus high nugget. High nugget means here, if I go back for this slide, okay, high nuggets means noisy data. And in the geostatistically rules, this nugget distant, the nugget distant should be from 10 to 30 relative to the range. So from 10 to 30 less than the range. In such ways, if your model come up with a maximum 30% of the range lag, okay, so you are in safe mode. Your model, it will be correct. If it will be more, so your data is noisy and it not need the variogram models. It will be conflicting your distribution. So be careful of such tricky points, and all of these solutions we will handle it in our course. In the last thing, vertical variogram, controlling the layering, because you already capturing the layering from the stratigraphic framework, especially if you are working in the heterogeneity reservoir. So you know very well from the well logs and zonation thickness the uncertainty, the thickness you have. Why fishes modeling? Fishes modeling is to capture geological heterogeneity and rock typing distribution that controls reservoir connectivity and the flow behavior. Actually, it ensures realistic property modeling, volumetric estimation, and dynamic simulation performance. This is the second questions that I told you before, and here is the answers. The fishes modeling, it's actually because the reservoir is not homogeneous. If the reservoir is homogeneous, no need for knowing the fishes. So each fish has different porosity, different permeability, different capillary pressure, and relative permeability, which is controlling the flow simulation after that. So without fishes modeling, you will assume a uniform rock with unrealistic flow behavior. So you will have a problem in flow simulation. Okay. Fishes also control the flow. Fishes control the porosity and the permeability, control the continuous property like especially porosity, okay? And the permeability, it will be linked to porosity. So in even thin shale tricks can create vertical flow bottlenecks, which it will affect on the dynamic simulation, and he will come back to you from where this come, okay? So you need to handle all of this to expect the flow simulation on it after that. Fishes define connectivity, okay? Fishes modeling define sand body continuity channel, connectivity, compartmentalization, flow barriers. So all of these, examples justify for you what is the importance of the fishes modeling. And also, it will improve the volumetric. Different fishes have different net to gross porosity, have different hydrocarbon saturations. So it's telling you where the good rock, okay, and where the barriers are. Where is the good rock? I mean quality. Here is the quality. And where is the hydrocarbon saturation respectful for this rock? So without fishes modeling, the STOIB, it will be biased, and the net bay, it will be overestimated, and you will have a lot of uncertainty. Different ways to model fishes here. Either you model through deterministic fishes modeling. At such point, you will have a polygon, you will have a volume that interpreted from the seismic data, for examples, used to control a spatial distribution or other. And this is an example, as I'm telling you, cross sections, just to show you how the lateral change in the fishes from area to area, okay? So if you go for deterministic, okay, such as, height, average, and distribution, something like that, it will give you one realistic approach. And if you go for the stochastic fishes modeling, because the area in between wells needs trend, needs algorithm to understand. But this algorithm and this technique should be matching with the geological sense, as I mentioned to you. So it depends on your variogram. that come from the depositional background effect, that comes from the surface outcrops background. All of such information gives you a conceptual model or a realistic conceptual model to populate the facies or to predict the facies in between the wells, especially in the area without wells, the well data. So stochastic here, facies are populating in the model using random sample probability distribution. If you don't know your object direction, if you don't know the facies kind and don't have a good proof for the facies modeling or prediction for the facies modeling you have, let software will not stop. Software will do for you the population whatever you need, but you have to guide him. You have to help him in order to have a good realistic model. Okay, once you go for the geostatistical facies, including some kind like sequential indicator simulation here, okay, this is populating using a variogram control. So I have some control. I have, as I mentioned to you, if you understand well the variogram algorithm, you will do a lot of time. You will do a lot of time trying in data analysis to adjust the variogram to make it a best fit, make it a best fit with your data available. Okay. Sometimes you need to assign values. This is I will tell you how we can do it if you don't need for the populating in some property. Different ways to model facies, coming back as example for sequential indicator simulation. And here the facies here is classifying, it's distributed according to the kind of distribution you have, either to go by deterministic. So deterministic here, you can assign value, you can iterative, even you can draw, you can have a seismic volume extraction indicator also. So once you have a Kriging, this is one realization, okay. Or you can go for the most common algorithm, which is a stochastic here. Whatever you are working for the pixel based, if you don't know the shape of or the positional system for the facies, so you go for the facies without knowing its directions, random, using the random indication, random Gaussian simulations. Or if you go for the carbonates to understand the trend and to guide him in the trend of the deposition. If you have an object base, if you have an object like a facies of fluvial facies, something like that, you can define the shape and you are going the distribution of the facies. It depends on your VPC. So vertical proportional curve for the percentage of the shale, for the percentage of the channel, for the percentage of the shale, the sand, I mean, he will capturing in all the channels, okay? So also you have a guide. You can go back for the VPC and adjust the percentage and come back here for the distribution. So the sequential indicator simulation, it's actually honorable data. It's capturing geological uncertainty. It's give you a multi-realization in order to capturing the uncertainty where exactly. So use a widely in reservoir modeling software like a Petrel or RMS for this kind of simulation. I will go again for deterministic approach. If you go for the estimation, indicator Kriging, this is a discrete distribution for probability, which honoring the well data so much, and they try to interpolate between the well data together in weight average interpolation mode, okay? Or you can go by direct addressing through assigned values. So if you know the values and you don't need for populate different kind of fishes or something like that, and for example you have clean sandstones and you have a big thickness, so you know already the fishes, it's a shore-based fishes having a sand, so you can assign the value Even you can iterative, you can draw sometimes your well data is not capturing exactly the channel, for example. So, okay, and you know the channel from the seismic data. Okay, so you can draw it through as in seismic interpretation, geobody, I mean, or you can draw it even here, if you know it, if you know the shape very well from the conceptual model, or you can use it in multi-realization in order to imagine the positional system, in order to imagine the distribution, how it's come. Because in our model, we are saying, no, if you can't draw it, you can't model it. Okay, so everything it should be drawn either by seismic, either by propagation, in order to model it. Okay, so and there is actually a learning system here, artificial neural network, but it depends on the train estimation model process. So it has to has different kinds of train estimation model process in order to help the software to come up with proper distribution for the fishes in deterministic mode. In stochastic mode, okay, you have a sequential indicator, a sequential indicator simulation. You have, this is what we exactly talked about it, which is honor the data, and for sure it will be using variograms and variogram trends, okay? You have truncated Gaussian simulation, and this truncated Gaussian simulation, it's using when your object, it has different shape, it's disappear in some area and having a repetition appearance again. So it depends on your fishes. You can decide which algorithm you are doing for the populate the fishes. In the pixel-based, actually, there is also truncated Gaussian simulation with the trend. It will use it for the carbonates. And also you have multi-point fishes simulation. This is what it will be advanced technique, because you are training the image described as special correlation from one point to different kind of points to try to find the relative position for each point. It is also advanced technique for fishes interpolation and the distribution. And for the object base here, we have general object for lovial, something like that. And you can, or geobody, also you can populate your fishes. This is an example from SIS, sequential indicator simulation results. But in this one, it's random, okay, because you don't know the shape of the fishes you have. This come without any variogram algorithm. So I'm just telling you how it's shaped in your models in different compartment of your structural grids. So the workflow here, if you need to multi-realization in order to capture the uncertainty, sometimes you are using most likely fishes, maximum fishes you have. Sometimes you are using the probability of the most likely fishes, or if you're using a population per each cell. All of those integrated together with the input hard data from the fishes distribution in order to come up with the fishes distribution at the end. So different realizations will give you different uncertainty in order to capturing the real data as much as you can. The third question here, why petrophysical modeling? Because as I mentioned to you, the wells are not spares. So this photo in the 3D visualization for the wells, you have two vertical wells and one side track. So in between the wells, okay, see the wells locations, it's our spares. We only measure porosity and the permeability at the well location, okay? But reservoir extends away. So how we can capture it, how we can model it, okay? So petrophysical modeling allow interpolation between the wells trying to honor as much as can the geological trends for generating a 3D probability distribution. It will help in controlling volumetrics because, as you can see in the equation of the Stoichkov calculations, it's mainly depending on the continuous property like net to gross, like porosity, like water saturation. We will discuss about those in the next slides. But the most important one is the porosity. So any error in property modeling directly impact on the reserves. It also controls the flow in dynamic simulation because it's strongly linked to the permeability. And the permeability distribution will affect the vertical permeability, 𝗂𝗃 for the vertical direction and the horizontal direction, okay? Especially in the heterogeneity pattern of your reservoirs. Saturation distribution, it will affect also, because if you have to model with the same average permeability, okay, but different spatial distribution, they will behave very differently, okay? So it controls the capturing the reservoir heterogeneity. Petrophysical modeling reproduce this actually variation using the geostatisticals and using the variogram algorithm, okay, as we talked about, and the trends and the phase control, because you cannot go for the petrophysical modeling until you finish your phase modeling, because the phase is telling you what rock is present, okay, but the petrophysical modeling tells you how good that rock is. For the deterministic actually approach in the simple interpolation between the wells for the porosity, it depends only on the weighted average interpolation, or you make a sign based on object type, or you make a sign based on the facies type. Because if your facies, you can make a sign value and let the software follow this, which is less realistic, especially for heterogeneity reservoir. But for stochastic, which is most common and better than deterministic in such area, in such algorithm, I mean, like sequential Gaussian simulation or Gaussian random function simulation, this is actually honor well data and capturing variability and generate multiple realization for uncertainty using the approach of the variogram. Because in data analysis, you have identified the variogram for phases, and then you have identified for porosity, and any property you have to identify its variogram, because it's a value different than others, okay? So the porosity modeling tells you how much storage capacity exists in each grid cells. In each grid cells, per what? Per each zone, okay? Per each layer even of the reservoir. The modeling way actually for the porosity, either because we are discussing here about the continuous property. So the modeling way either deterministic or stochastic. So if I going for deterministic, I will go for the Kriging algorithm, and the Kriging algorithm is simple Kriging, ordinary Kriging, universal Kriging. So the limitation here of any deterministic, it will smooth the underestimates variability. So it will smooth the models, okay, and it will come with one realization only. So this is because it's averaging, moving averaging what you have from the well data. But the sequential Gaussian simulation, which is most common even in continuous property like porosity, it's preserve actually the heterogeneity, reproduce also again the multiple realization that will help you in uncertainty analysis after that. And as you can see here, this is a regenerate local variation sequential Gaussian simulation for the see the difference here is totally different between stochastic and deterministic. Which is right? Which is wrong? We are not sure. We are not sure this is right. We're not sure this is right 100%. But the percentages of this what right for multiple realizations, it will be have a good, even if it is matching with the geological understanding, if it is matching with the geological sense, so it will have a reliable as much as we can nearby the real data. So the porosity modeling workflow, starting from the well logs, okay, going through upscaled the cells that respect, the high resolution log data for each. See, this is half feet log data, okay. Then we are going for the property variograms, trying to reach the maximum variance, try to get the the match as much as you can. After that, you are going for the histogram to define the relationship between each facies and see the upscale relative to the well log data in order to come up with the 3D facies modeling for using in porosity modeling. And the facies and the porosity should be related to each other, because this is a must, should be related to each other. For permeability modeling, the permeability here is linked to facies and the porosity, okay? Limited core permeability measurements. This is the limitation of the permeability, because sometimes it's difficult to model, to be fair with you. Stochastic cloud transform try to capture data scatter range. This is actually the cloud transform between porosity and permeability, I mean. You will have a diagenesis matrix. So permeability tends to be difficult to model. If you have this diagenesis matrix, so you need to remove the effect of the matrix in order to understand the larger scale, which is the fracture contribution. The fraction contribution for the permeability. Okay, so from where you got this information? From the well test. Okay, so the permeability from the well test is calculated and by analyzing pressure response data obtained during controlled production or injection. So from well test, you can know from the flow meter here in such example, you are knowing the permeability thickness. You can have an idea about the average permeability at each well, and you will have an evidence for large scale to understand the fracture contribution with you if you can remove the effect of the matrix from the total, okay? There is a beneficial point here helping, the geoscientist, which is the barriers, because it depends on the length of the test and the radius of investigation. They can detect the barriers, because sometimes in seismic resolution they cannot capturing the minor fault, and the permeability test, okay, from the well test they can capture there is some barrier, or they can validate your fault, okay, if it is very nearby the well. This is one of the integrated G&G data here. So I have a question here. Why flow shouldn't occur at irreducible water saturation? Okay, so I have answer also. At irreducible water saturation, it should be the water mobility should be zero. There is no movable water saturation. Why? Because there is no water flow should occur. The only oil and the gas should be mobile. So the challenge here, if the reservoir engineer telling you, I have a flow, so there is something wrong in your setup. So you have my solution here, static model solution. You have to check to the rock typing even, because if you can see here the curve between the porosity and the permeability, you have in this value of the porosity, you have different values of permeability. However, you have one porosity function, different kinds of permeability. Okay, so even if you have a sand, okay, this sand can be categorized, can be divided into parts. Okay, so you have to reclassification the rock typing you have, even if you need to classify the porosity range. So you need to have rock typing here, okay, that having one value of permeability, you having rock typing here that having two types or two values of permeability, and the third rock typing here. In such way, you are telling the reservoir engineers, okay, try to avoid this value in order to avoid the water mobility, okay, the flow of water. So once you are checking your rock typing, you will help the relative permeability calculation for in your static models to be misunderstand or mismatch with the flow simulation. And also sometimes you have cell thickness, very small cell thickness in stratigraphic layering. You have in on labbing, on truncation, something like that. It will affect on the model because it will have a value. Okay, so I know there is a solution from the dynamic reservoir engineer for such issues, but try to avoid these problems before going for such problems in your static model, I mean. In such these cell thickness and geometrical problems we will also handle in our course. This is one of the critical point in static modeling. Try to neglect any negative cells. What about the net gross? The net gross here is linked to facies, and linked to porosity and permeability. In a static model, okay, net gross is often derived from well logs. So it's okay now. It's upscale into simulation grade blocks. We can do it very easy, okay? Net gross ranged from 0 to 1. Yes, agree. But what is the needs in the modeling or not? So if porosity from logs over gross interval, if you are collating the porosity from the logs over gross interval, so no need for net gross. Of course, simulation cells, if you are working in the course simulation cell, big cells with a net only properties, so yes, you need to apply the net to gross probability distribution, okay? If you are working in the fine grid, includes shale cells, if there is a shale cells, so no need for net to gross, okay? If you are working in the porosity in the net sand only, okay, so yes, you need to net to gross, because you don't need as I mentioned to you, in some sand, in some fishy sand, it has a different permeability within the sand itself. So the rock typing will be changed at that time, and at that time you need to apply the net to gross. What about the water saturation? The type of water saturation: initial water saturation, irreducible water saturation, and the movable water saturation. Initial water saturation, the water present before production, okay? So in such way, it's equal irreducible water saturation in the hydrocarbon zones. So in such a way, if you have this one and the BVW, this is bulk volume water. It will be estimated from SW using the porosity. If it is a constant, if the BVW, the bulk volume of water constants, so at that time you will not need for populating water saturation. So you will give it a sign value at the oil water contact, and no need for the propagation, which is called equilibrium approach. So if and you can determine the water saturation from the log and the capillary curves. Okay. Right. What about the irreducible water saturation? This is irreducible water saturation. This is connected the pools. Okay, water connected the pools, which is a minimum water saturation you have, and this water for sure it's immobile. It's not movable, okay? So this is 0, okay? So in such way, if the BVW, okay, is constant, okay, no, the water saturation equal the irreducible water saturation. the initial water saturation. The initial water saturation equals the water saturation itself, so no need for doing propagation. So, and the movable water saturation here, the water saturation itself, if you remove the initial water saturation, the water will move. Suppose if you have water saturation, water saturation is a 50%, and you have initial water saturation is a 30%, so the 20% will move. Okay, so once you have an input porosity, okay, you have to check your BVW against the initial water saturation in order to come up with a function of porosity, in order to come up the BVW value function of porosity to understand and to tell the geomodel, I need to make equilibrium approach, no need for doing a propagation for water saturation. But for history match, for water flood estimation, for dynamic studies, you have to have numerical approach and you need to propagate the water saturation. So it depends on the BVW. If the BVW is constant, no need, and you go for the equilibrium approach, assign value for the zonation, and assign value, just one value, I mean, for all the cells, like that, water context, for example, like that. If not, and the flow simulation telling you there is a flow, okay, there is a flow from the water, so you need to understand through doing your analysis from the porosity input as a function for BVW, the bulk of volume water, to propagate the water saturation. For the time being, now we are finalizing the properties. We are discussing now for the properties, the phases, porosity, permeability, net growth, and water saturations. Okay, let's go for the modeling, starting with the volumetric calculation first, and uncertainty analysis, and then we are going for your questions. Volumetric calculation principle, since each cell is triangulated, so you are cutting by the cell exactly at the contacts, and you know the contacts from the cells. The input needed for volumetric calculation, this is a 3D grid. So if you need to calculate the volume for each zones, for each segment, in your models, you can calculate it after defining the contacts. You can go for the volumetric calculations and adjust the contact and do your volume calculation. It is possible to generate a contact property and making different realizations. In such way, you will have an result like Monte Carlo simulation, because here you will have but this is in 3D now, so you will have the 3D property with different values for each of the hydrocarbon interval after your calculation for oil in place or recoverable oil, whatever you need. You are doing different realization of the volumetric calculation in the static model. How you can QC your model? As I told you, it's a big pictures and iterative workflow. You are going for the well and seismic data, going for the proportion of the phases, structural model, stratigraphic framework, upscaling reservoir grids, and production forecast. And you are going, even if you have a 4D seismic data, you can come back to the modeling and update. So it's iterative update. The key message here is the static model is only as good as a seismic and structural inputs. Seamless integration and the continuous feedback ensure the reliable geological and engineering model. In history match, also it's an iterative approach. Once this is initial geological and simulation models, and you have new update from the permeability to achieve the history match, then you go back and update your geological and simulation models. So static model define where flow should happen, and dynamic model calculate how much flow happens. This is a short answer for the difference between a static and dynamic model. There is also a good point because if you are drilling a well and you need to update the result of such well within your static model without need to go back from the beginning, from the horizons and the populations. You can make a local update. Can be seen here. It's you can define, the radius around the update of 1000 meter around the well in order to update the cells and the population for fascias, for porosity, for or for all the property you have already modeled in your static model. So this is one of the advantages here. You have local update of the model. The uncertainty analysis here, this is a very important part in our webinar. Actually, what you can see here, and this is actually matching the reality. Here you have 8 structure models from a set of 400 models representing structure uncertainty. Okay, so different interpretations give you different models. Okay, so faulted top structure, this is a case 4. But during this analysis, we have 4 bottom models have the same interpretations of the model 4. Okay, so this is different realizations, but actually it exhibit a different top horizons with little difference. So this is one of the uncertainty pitfalls. Actually, these cases can grow as n factorial. Yeah, that means this is one of the uncertainty analysis. Sorry. Do you have do you see my screen?
Yes, we can see your screen.
Yes, I have some problems. I don't know from where it's coming. It's switching off, switching on. Maybe from my Vega. Okay, so you can see my screen now?
Actually, not right now.
Okay. So this, I'm discussing now data uncertainty analysis. Do you see my data analysis, uncertainty analysis now?
No.
No.
Well, I cannot see it. I don't know if maybe you can just in case stop sharing,
Stop sharing
everything and then share again.
Yeah, sure. Just a minute. So now you can see my screen?
We can see the paint.
Yeah. I'm trying to So you can see the presentation now, right?
Yes, now we can see your presentation.
Okay,
Modeling, QC, and volumetrics.
Okay, very well, very well. So this is uncertainty analysis in the volumetric calculations for the different kinds of structural models. And once you have the match between 4 models, now you can measure the uncertainty. This is another example from multi-realization analysis from the porosity. Okay, so in such okay, so in porosity here is 10 geostatistical realizations, different cutoffs, 5 cases, velocity models, 4 cases, bulk volume water, 3 cases, oil water contact, 3 cases, and just one single capillary pressure equations. And this is also one of the data uncertainty analysis. But now you can capture the uncertainty. Where is the uncertainty coming from different realization? Data uncertainty analysis also, this is a mapping of multiple realizations depending on the facies distribution in order to capture also the uncertainty. All of that for such a tornado chart result from multiple cases in order to know where is your uncertainty come. This is one of the important slide in my webinar, concluding the static model uncertainty analysis, showing for you the maximum uncertainty come from the area of closure. That means it comes from the structure, okay? So it's telling you the decision to go and refine your structure modeling and they come back again, even so you have also 11%, 12% almost from porosity, and a very minimum from uncertainty analysis for fill, okay, and hydrocarbon saturation. What we can do, this is the most also important questions for the reservoir management. So we have in each item for gross rock volume, oil price, average porosity. So this is the uncertainty analysis and impact on MBV. And the action here, we can buy new seismic for the gross rock volume in order to reprocess the imaging and adjust the structure input. Sometimes you need to make a different rock model for your saturations. You need for net to gross more gamma rays. You need to adding more data in order to compromise your modeling and reduce the uncertainty of the net to gross and the continuity. Volume calculation principles. This is okay. Again, sorry. This is coming here. Yeah. The last slide here to having to reply your questions. What should you remember? Models are collective of cells or boxes filled with the numerical data. Modeling is a team effort. Models should be fit for purpose and carefully planned. Your objective, as I mentioned to you, most models built as input for fluid flow simulation models. A good model captures the reservoir's key flow characteristics. Stochastic methods are preferred for distribution of the rock properties. And we have to have steps in the modeling. We have collaborated stuff and plan project, gather and QC input data, build the framework, build the fishes modeling, build the rock property modeling, and then you can evaluate your model through uncertainty analysis, and then using this model as an input for the fluid flow simulation, well planning, volume, and false analysis. Thank you for attending my webinar. I hope I can deliver for you a good information that will help you in your geomodeling and understanding and uncertainty analysis. Thank you all for attending, and let's start with replying your questions.
Thank you, Mr. Mohammed. Yes, just you can check maybe in the chat section. We have
Yes.
some couple of questions from our attendees.
Good, very well. What is the minimum scale of petrol required for developing the 3D model? Can a geologist with basic skill in petrol can do 3D modeling efficiently? The minimum skills of petrol, what do you mean of petrol required? You need, if you need the of petrol required, minimum skills of petrol, minimum skills you mean for your experience, okay? For petrol specs, it depends on your software. If you are asking about the specs of the software, yes, the minimum specs, it will be you know, going for the RAM of 16 RAM, and you are going with the Vega for 4 giga. This is the minimum specs you have, and you should have a good processor and the good type of Vega like Quadro or something like that. Can a geologist with basically skill in petrol can do 3D modeling efficiently? Yes, for sure. The geologist and geomodeling can basically will have actually they can do it very well, but it needs a cooperation between multidisciplinary, as I mentioned for you, between the geophysicist, petrophysicist, and sedimentologist. It's not actually an easy for you to finalize the full picture of the modeling. But for you as a geologist, you can do your structure part. And once you are going for the population of fishes modeling, or you need to populate your property within your structure framework, you need the cooperation between the different disciplines team. So I hope I replied your message. Thank you so much for the detailed lectures. How can we propagate this methodology into fractional and the DFN modeling, especially in the carbonate context? Yes, yes, there is a different ways in carbonates, but we are discussing here, you know, the algorithms for generally, okay. But if you remember, one of the algorithms we are discussing, mentioning for you the trend. So in carbonates, it requires trend, and you know, I will tell you sometimes I will show you sometimes in variograms, okay. Sometimes in variograms, this is the different kinds of variograms, and all the variograms methodology going for such cells and going flattening, okay. In carbonates reservoirs, actually there is actually similarity going, even once you go deeper, the similarity becomes still with you. So you have a trend. You have a trend, okay. So in order to detrend your model, there is advanced tools. We can discuss it actually more detailed in carbonates. So you have to stop your trend as telling your software, I have a cell here. Stop searching for any variance after this point. So there is a different ways with the carbonate, but it can be, but it will be different than this algorithm, because carbonate, it has a trend. So it may use also the help of the seismic data. We are at the break now, okay. Sorry, I didn't capture you once you telling me listen properly. My voice was not clear because I have some, you know, notes here. Could you please check your connections? Is it still sharing pink screen? Yeah, we are passing through all of these messages before. Yes, how a deterministic and the probabilistic model differs. Okay, how and based on what I will select the minimum, mean, and the maximum of the properties. Yeah, very good questions. So as I mentioned for you, there is a difference between deterministic and probabilistic model differs. Deterministic, and you mean stochastic, okay? Because stochastic, it gives you a probabilistics. Deterministic here gives you one realization, okay, one value. But probabilistics, it gives you different realizations that you can. This is very important. So I will show you. Yes, here. This is a porosity, okay. 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 Let's go for your questions. Yes. This I will show you examples here. Okay. This is an example for the porosity. Okay. This is a deterministic distribution, and this is a stochastic or probabilistic approach. Okay. So deterministic here, it's a kriging. It's a red curve here. See, it's integrating between the wells data as averaging, okay? But the probabilistic, it has two simulations, starting from here to here, going high and then going low to reach it to the another well data. And there is a second realization going down, going for the Yule data. So in all the cases, we don't know which one is correct, But in heterogeneity reservoir, okay, there is some sort of heterogeneity you have. So the different realizations it gives you, it's try to near by reliable depositional model or understanding of the geological difference between the well data. If you have a seismic data will help more. If you can doing your advanced integration will help more and more, because as we mentioned for you, you can extrapolate your porosity volume from the seismic inversion data using the model-based inversion. So in such way, we'll try and you will judge which realization is nearby seismic, and you will take it in your modeling after that. This is the difference between deterministic and the stochastic. How and based on what I will select the minimum, mean, and the maximum of the properties. So minimum and the maximum and the mean of the properties, if you are working, it's already captured in the modeling. You get my point? Because as I mentioned for you, if you are using with the geostatistical approach, okay, for example, this property is a porosity like that, okay? So you have different realization. Sometimes it's high, sometimes it's minimum, sometimes it's mean, okay? It depends on the algorithm you are doing itself, okay? So if you are going for if you don't have a seismic data and you need to go in a smooth way, you are going for deterministic way, and at that point it will be the mean approach here. So, but if you need to go for the maximum, you can select the maximum realization that respect the higher value, okay? But you have to see the seismic data and ask a geophysicist about in between or the derivative properties from the seismic inversion. It will guide you very much in this. I hope also to answer your question very well. Okay, between pixel-based and object-based, which one is the best? It's not which one is the best. The pixel-based, it's actually used, I will show you, in the facies modeling, because it's the object-based, you already know your object from understanding from the seismic data, from the well data you already know you have a fluvial channels in this one. In the pixel base, you don't know. You get my point? You don't know the shape of the facies. So you are working with a random sequential simulation to catch. But if you know from the seismic on the from the your background, the shape exactly of your object, so now you are working with the object based. But for sure, if you know your object, it will be better. You get my point? But as I told you, the question is not come which one is the better. The question is when we use pixel based and when we use object based. We use pixel based if you don't know the direction exactly of your facies. But if you know your facies, you are going for the object based. In the presence of 4D seismic data, is the integration possible at the static modeling? Yes, for sure. The 4D seismic data, actually, it's a monitoring for the data to understand the context, to understand, what's happening in the amplitude if you are working in the gas field or something like that. And yes, it will, as I mentioned to you, this is actually iterative workflow. And we already covered in our webinar the 4D seismic data. Yes, here. So the integration of the 4D seismic data comes here, telling you if you have any information update, you have to have going back to the geological and the simulation models to update. So it will be so much beneficial also. So because the 4D signals are usually as a result of production and injection activities between base and the motor. Yes, for sure. Yes, I know exactly the benefits of the 4D signals, but it will have if you are working in the gas field, the 4D it will represent for you as if you are working with the new data, because the gas effect it will minimize in your seismic amplitudes, and your calculations and your assumption in the seismic inversion and the EVO it will be different, especially seismic inversion output, especially acoustic impedance that related to the porosity. So the porosity related to the continuous property. So it for sure it will link to for the relative permeability that will affect on the flow simulation. So it's integrated information together. So for sure it will affect. Okay. Thank you so much. What is the difference between cell volume and the cell inside out? Okay, as I mentioned to you, the cell volumes, okay, you are after you are doing your model resolution, you are setting with the RE data, okay, and see how much cells in your model, okay. After classifications, it depends on your data. It depends on your information from the geology. What is your objective? Where is your reservoir? Is your reservoir in heterogeneity formation? So you have to add more cells in such zonation in order to come up with more detailed information in the modeling. But and this is the kind. But there is actually QC for the cell inside out, or cell deformation of the cells. You have to make a QC before going for the stratigraphic boundary. You have to check your cells very well in order to avoid any negative cells and remove it from your model. Thank you so much for good words. Yes, your course be sufficient enough for fractional modeling and your course. I will add the fractional modeling. Yes, okay, no problem. I will add the fractional modeling in order to understand. It will be very heavy for me, but I will add it, no problem. How to perform a QC on grid cell geometry to avoid simulation problem. Okay. Yeah, I mentioned for you how to perform QC on the grid. And cell geometry, I already answered these questions to avoid the simulation problems. Yes, cell geometry, actually, there is a workflow for it to check the negative cells to remove it from the models, okay? The QC on the grid, it's much important because it takes so much time, especially during the pillar grading process. Pillar grading process, because once you apply the skeleton, top skeleton, mid skeleton, the base skeleton, and you have truncation faults, the shape of the cells, it will deform so much, and it needs a QC very well. It needs to align direction for each fault, okay, that avoid this deformation. So it depends on the direction of the fault itself. You get my point? So especially if you have, I'm discussing now about the truncation faults together. Fault truncated to each others will have a lot of problems in the cell geometry. So you can solve it in the pillar grading process through adjusting different kinds of directions on the faults to tell software try to handle these cells along this I trend or K trend or G trend, okay? Even in sometimes you are doing this trend as a boundary or the segment for your model. There is a lot of solution. It depends on the shape or deformation of the cells, especially nearby the faults. You didn't discuss about fracture, how to incorporate fracture into 3D static models. Yes, we can discuss it in our course. Yes, it will take so much time. That's why I prefer to go with the step-by-step basics, and the fracture actually modeling. It will have a separate webinar and maybe a separate course, but I will involve it in my course, inshallah, for bigger understanding for you, for all of you. It's a very information and a good lecture. Thank you so much. I appreciate your words. Thank you for great summary and presentation. What is the importance of static rock type in 3D modeling? Yes, this is a very good question. Thank you for this. As I mentioned to you, the rock typing here, we already covered it in our webinar, especially in the permeability. Once we have this problem in the flow, okay, and we don't know where is come this flow, so it needs here to define the rock typing. The advantage here on the importance of the static rock typing in the 3D modeling is telling software to help him during propagation of the properties or even the fishes to define the rock typing that have porosity and permeability values. Okay, so here in such examples, there is one rock type, and I have a problem in the flow simulation. So coming back to redefine the rock typing in respecting, the value of the permeability that come from the well test. Okay, even if I know it from the production. So this is a good beneficial here. So this is the rock typing here, respecting the different values of porosity to avoid the problem in flow simulation. So this is one of the importance for rock typing, even for population in the properties and the fish's diagenesis problem. If you have, can I apply a net cutoff by calculator after distribution and before volumetric? Yes, you can apply the cutoffs by calculator and distribution and before volumetrics, but it should come back. You should redistribute your property again, because the cutoffs here it will cover the continuous property like a porosity and the water saturations, but you already have a distribution for the fishes, and once you adjust the cutoffs for the continuous property, you can redistribute the property again before volumetric. Yes, you can. Thanks so much. Can we have the recording video or material of this good presentation? Thank you. Appreciate your words, excellent presentation. Thank you so much. Yes, thank you all for your questions and interest and these good words for me. And hope to see you, all of you, in my courses. It's not a marketing for sure, that I'm telling you what I'm going to add in my courses. I will cover again all these theoretical points. In addition, we will have a workshop. This workshop we'll do it live together, okay, using a special platform that we can agree together on it. And also there is videos for each step. I can do it from the structure till volumetric. So we will do it alive, and we will have a video for each step after the course, in order to, if you if you forget the steps, you will have it and you will remember from the course, inshallah. Thank you all for attending, and thank you for good words.
Thank you. Thank you. Thank you, Mr. Mohammed.
Appreciate
Thank you, everyone, for your time and attention. Also, thank you for the questions that you've been doing. We truly appreciate for joining today. A very special thank you to Mr. Mohammed again
Thank
for
you.
delivering such an insightful and valuable presentation. We truly appreciate your expertise, that you're sharing this expertise, your knowledge, and you didn't hesitate to share all that with us today.
Thank you.
So thank you so much.
Thank you.
Just to answer your question about the recording, you can find this recording in our YouTube channel of Mega Plus and Oil and Gas Solution. So you can go there, visit us, and watch the video again. We look forward to connecting with you again soon, and have a wonderful afternoon, evening. Thank you. Goodbye.
Thank you. Thank you so much.